Problem number 17. We have a three-dimensional region R. That is the region above the plane z is equal to 2 inside of this sphere. So it looks something like this. And that z is equal to 2, and there z is equal to 4 up there. So that filled in region, three-dimensional region. We want to find the outward flux of the vector field F written here. So it's the integral over the boundary of R of F dot ds. So this is a really complicated vector field, and we'd have to, parameterize two different parts of the surface here to do it straightforwardly. So fortunately, we have the divergence theorem to help us. So instead of doing this, we're going to compute the triple integral over this region R here of the divergence of F. What is the divergence of F? Well, first we take the partial derivative with respect to x of this, which will be 2z minus 0. Then we need the partial derivative with respect to y of this, which will be 0 minus 1 over 1 plus y squared. And then plus the partial derivative with respect to z of this, 0 plus 1 over 1 plus y squared. So that's the thing we're integrating. Oh, look, those two things are canceling out. The integrand is just 2z. Okay, so now we have to integrate this. How are we going to do this? Honestly, we could set up this integral in either rectangular coordinates or cylindrical coordinates or spherical coordinates. All of those will be okay to do. I'm going to do this in cylindrical coordinates. So what are the bounds here? The bounds, we would need bounds for cylindrical coordinates on theta and r and z. Okay, so we can see one full loop around the circle. Theta runs from 0 to 2 pi. Okay, what else do we have here? So what is the biggest that our radius can be? The biggest our radius can be here is when z is equal to 2. And so that would turn x squared plus y squared become r squared plus 2 squared is equal to 16. R squared is equal to 12. So the biggest our radius can be is the square root of 12. Smallest, of course, is 0. And then z, for fixed values of theta and r, the smallest z can be is 2. And the biggest z can be here, we again use r squared plus z squared is equal to 16. Solving this for z will give us the square root of 16 minus r squared. We want the positive square root because z is clearly positive above the xy plane. Okay, so this is what we have here. So let's write out our integral. Theta runs from 0 to 2 pi here. R runs from 0 to square root 12. And z runs from 2 to the square root of 16 minus r squared. Our integrand is 2z, and then we throw in the factor of r. That's the Jacobian for cylindrical coordinates, dz, dr, d theta. Okay, so what do we have here? Let's see. That will just give us a factor of 2 pi right there. And then integrating with respect to z here will give us r times z squared, and we're going to plug in z from 2 to square root of 16 minus r squared. And then we'll have one more integral to do with respect to r. And let's see here. So this will be integral 0 to square root 12 of r times this squared, which will give us r times 16, minus r squared times r is r cubed, minus what we get when we plug in z is 2 here, so that would be 4r dr. Okay, so then at this point, to finish off this problem. This will be 2 pi times. This becomes 12r minus r cubed. And so the integral antiderivative of that will be 6r squared minus r to the 4th over 4. Plug in r from 0 to square root 12. And so we have 2 pi times 6 times 12 minus root 12 to the 4th will be 144 over 4. And that's a perfectly good final answer.